Hello, Honors Math 2. Let's see, hopefully you've already tried all these problems, so this is just a quick run through so you can check your solutions and I can answer any of your questions. So if you're asked to find the inverse of this function g of x, rather than undoing the operations like we used to, I would probably just use our algebraic method, which does undo the operations. So you take this, rewrite it as y equals. The inverse is this. When I switch x and y, that's the inverse. And then I'm going to algebraically solve for y. When I do that, I do undo the operations of that original function. To get rid of that 2/3, I'm going to multiply both sides by 3/2. That's easier than distributing, so those are gone. And I'm left with 3/2 x is equal to y plus 4. Subtract 4 from both sides, and I'm left with 3/2 x minus 4. So the inverse is g inverse of x is equal to 3/2 x minus 4. Alrighty. What did you do with number 2? If you're given this function f of x equals 2/3 x minus 5, could you evaluate f inverse of negative 13? Remember, if this is an input on the inverse, that must be an output on the original function because inverses reverse the domain and range. So, for what input, for what x value, input is 2/3 x minus 5 equal to that would be an output of negative 13. And solve. 2/3 x is equal to, add 5, I get negative 8. Multiply both sides by 3/2. And my input, my x value, would be negative 12. So an input of negative 12 gives me an output of negative 13. On the inverse, an input of negative 13 would give me an output of negative 12. Because of that reversing of the domain and range. Alrighty, let's keep checking. If I'm given this function p of x, what is p of a plus 3? That's just practicing our inputs for functions, and we saw compositions of functions in this module, so I'm going to input a plus 3 wherever I see an x. And p of a plus 3 is equal to negative 2 times a plus 3 squared plus 8 times a plus 3. Don't forget minus 3, which is equal to negative 2 times, I'm going to square this thing, which is a plus 3 times another a plus 3, which is a squared plus 6a plus 9. Distribute that 8. Plus 8a plus 24 minus 3. Combine like terms, and p of a plus 3 is equal to, oops, not yet, I have to distribute. Let me pause. I distributed here. I combined 24 minus 3. Combine like terms one more time, and negative 2a squared minus 4a plus 3 is p of a plus 3. Alrighty. Speaking of composition of functions, here's a little review of some composition of functions. Remember, we work from the inside out. So I'm curious what q of 1 is. Q of 1 is negative 10 times 1 plus 25, which is negative 10 plus 25, which is 15. So really I want p of q of 1, which is p of q of 1 is 15. And now p of 15 is 3/5 times 15 minus 7, which is equal to, what is that, 1, 3, 9 minus 7, and p of q of 1 is equal to 9 minus 7, which is 2. Alrighty, composition of functions. When I take the output of one function and use it as an input into another function. I can plug an entire function into a function. So remember that notation, that's the same as p composed of q of x. P composed of q of x. So p of q of x is the same as p of q of x, which is negative 10x plus 25. And now I plug that whole function into p of x, which becomes 3/5 of negative 10x plus 25 minus 7. So what is that? 5 goes into 5 once, 5 goes into negative 10, negative 2 times, 5 goes into 5 once, 5 goes into 25 5 times. What is that? P of q of x will be negative 6x plus 15 minus 7. P of q of x is equal to negative 6x plus 8. Composition of functions. Alrighty. Okay, here's another case where the input into G prime, slipped into calculus mode. An input into G inverse is going to be an output of the function G. So I'm going to ask myself, when is x cubed minus 7 equal to an output of negative 15? Stop and solve that if you have not. The output of negative 15 occurs at, add 7, cube root both sides, I get negative 2 for my input. So on the inverse, an input of negative 15 is going to give me an output of negative 2. Alrighty, next case. Find the function, here's my function f of x is the square root of x minus 4 plus 3. Can you find the inverse of that function and its domain and range? Well, I might make my life easy and find the domain and the range for this function first. Remember that I can only plug positive numbers under that square root, so that means that x minus 4 has to be positive, greater than or equal to 0. X has to be greater than or equal to 4, so the domain of the original is from 4 to infinity. If I refresh my memory what that function looks like, it's a hook, it's a square root function shifted to the right 4, 1, 2, 3, 4, and up 3. So that's my original function, f of x. Alrighty, notice the domain that checks out is 4 to infinity. The range starts at 3 and goes up, so that's 3 to infinity. What's the inverse of this function? I don't know. I'm going to find the inverse. So y is equal to the square root of x minus 4 plus 3. When I rewrite with y, I switch the x and y, and I solve for y. I subtract 3 from both sides. Then I square both sides to undo that root. Left with y minus 4 is equal to x minus 3 squared. Add 4 to both sides, and y is equal to x minus 3 squared plus 4. So the inverse of that function is x minus 3 squared plus 4, which is quadratic. But remember, the range of my original function becomes the domain of my inverse, and the domain of my original becomes the range of my inverse. And that's a quadratic, which moves, what is that, to the right 3, 1, 2, 3, up 4, but only from 3 to infinity and a range of 4 to infinity, and there's my f inverse of x. And that should make this more clear. Here is my function, f of x. Remember, the inverse can never have more points on it than the original function. It can't get larger, a larger domain or range than that original function. Alrighty, let's keep going. Oh, rewrite this in logarithmic notation. This is where I same, base, switch it. This is perfectly equivalent to log base. The base of my exponent becomes the base of my logarithm. Switch. The 8 was with the m, now it's going to be with the p. Those two things are equivalent. Two different ways to write the same thing, exponential or logarithmic. Find the inverse of this function. Okay, I'm going to rewrite this as y is equal to the cubed root of x minus 2 plus 9. I'm going to switch the x and the y. y minus 2 plus 9, and take a moment and solve for y. Alrighty, subtract 9, cube both sides, add 2. I isolated y, so that means h inverse of x is equal to, what is that? X minus 9 cubed plus 2. Alrighty. Now what? Evaluate this logarithm. Okay. What does that mean? That means what does log base 3 of 243, what does that equal? What would that number be? I'm going to rewrite this. I'm going to same base switch it again. And this logarithmic means 3 to what power equals 243. When I rewrite this exponentially, same base, the base is going to be 3, but now I'm going to switch. I'm going to just make this an x, and the 243 goes on the other side. So that's rewriting that exponentially. Then 3 to the x equals 243. 3 to the x, 243 is 3 to what power? Is that 3 to the 5th, I believe? Yeah, 243 is 3 to the 5th. So that means that x is 5, and that means that that value is equal to 5. For this one, I just graphed that line g of x, y-intercept of 3, and then a slope of down 1 over 4, down 1 over 4. And then I just reverse those ordered pairs. So if that's 0, 3, 3, 0 is on the inverse. If that's, let me count, 4, 2, 2, 4 is on the inverse. And that is 8, 1, 1, 8 must be on the inverse. And here's a graph of my inverse function when I switch the x's and y's. Here's g inverse of x. Remember, inverses always have that symmetry across the line y equals x, and you can see that with those two linear functions. I thought we could use a little more practice with these evaluating. What is that equal to? I'll just make that x. I don't know. I'm going to rewrite that exponentially. I'm going to same base switch it. The base of the logarithm becomes the base of my exponential. 2 was with the 1/64th, now 2 is going to be with the x, is equal to 1/64th. And now I'm going to rewrite these with the same base to see what x is equal to. Left-hand side stays 2 to the x, right-hand side becomes 2 to some power. To bring that 64 up must be a negative exponent, and 2 to what power is 64? That's a negative 6. So this thing must equal negative 6. It's the value of that logarithm. Alright, here's good practice of finding the inverse of a logarithmic. Do you remember the inverse of a logarithmic is exponential? And vice versa. The inverse of an exponential is logarithmic. They're inverses of each other. So to find the inverse of this function, rewrite as y equals log base 4 of x minus 1 plus 5. Switch the x and the y. X is equal to log base 4 of y minus 1 plus 5. And now solve for y. X minus 5 is equal to log base 4 of y minus 1. The subscript, that 4 is lower. Everything else is even. That 4 is written lower. How do I get a y out of a logarithm? I rewrite this exponentially. Same base switch it. The base of the logarithm becomes the base of the exponential. 4 was with the y minus 1, now 4 is with the x minus 5, is equal to y minus 1. Waha! I just got that y out of the logarithm. I'm left with y equals 4 to the x minus 5 plus 1. So f inverse of x, the inverse of that function, sorry about that, inverse of that function is 4 to the x minus 5 plus 1, which confirms the inverse of a logarithm is always exponential. This last case should confirm that also. Start to graph g of x equals 3 to the x. And remember my key points on my exponential, and I sketch it with a domain of negative infinity to infinity, a range of 0 to infinity, and an asymptote of y equals 0. If y is equal to 3 to the x, find the inverse function. I'll pause. find the inverse, switch the ordered pairs, and graph. Thanks for